In this video, I will discuss the how to solve the linear programming problem by BTech method. Let's see the problem. Use penalty or BTech method to solve the following LP problem. Maximize z equal to 2x1 plus 3x2 plus 4x3 subject to the constraints 3x1 plus x2 plus 4x3 less than or equal to 600, 2x1 plus 4x2 plus 2x3 greater than or equal to the 380, 2x1 plus 3x2 plus 3x3 equal to 540, and x1, x2, x3 are greater than or equal to the 0. Let's see the solution. First step is convert general LP problem into the standard LP problem. In BTech method, if any constraint having the less than or equal to the inequality symbol, then add a slack variable. Similarly, if any constraint having the greater than or equal to the inequality symbol, then subtract a surplus variable, also add a artificial variable. And if any constraint having equal to symbol, add a artificial variable. In the given LP problem, first constraint having the less than or equal to the inequality symbol, so introduce slack variable, that is add a positive slack variable, consider S1. Second constraint having the greater than or equal to inequality symbol, so introduce the surplus variable and also artificial variable, that is subtract surplus variable minus S2 and add a artificial variable plus A1. Third constraint having the equal to symbol, so add a artificial variable, that is plus A2. Here S1, S2, A1, A2 are the greater than or equal to the 0. Now constraint will become the 3x1 plus x2 plus 4x3 plus S1 equal to the 600. Second constraint will become 2x1 plus 4x2 plus 2x3 minus S2 plus A1 equal to the 480. Third constraint will become the 2x1 plus 3x2 plus 3x3 plus A2 equal to the 540. Then write objective function in the terms of decision variables x1, x2, x3, slack variable S1, surplus variable S2 and artificial variable A1 and A2. Now objective function is maximize z equal to 2x1 plus 3x2 plus 4x3 plus 0s1 plus 0s2 minus ma1 minus ma2. Here 0 is the coefficient for slack variable and surplus variables, and minus m is the coefficient for the artificial variables. Second step is the find the initial basic feasible solution. Here variables are the x1, x2, x3, s1, s2, a1 and a2. So total we are having the 7 variables and we are having the 3 equations. So to solve these equation, initially we are considering the decision variables x1, x2, x3 and surplus variable s2 are 0. Then we have to substitute these values in the constraint equations. We will get the S1, A1 and A2 values. First I have to substitute x1, x2, x3 are the 0 in the first constraint equation. We will get the S1 value, that is the 600. Next I have to substitute x1, x2, x3 and S2 are considered the 0 and substitute. Then we will get the A1 value is the 480 Similarly, we have to substitute the x1, x2, x3 values are the 0 in the third constant. We will get the a2 value is the 540. Next step is the write the standard form of LPP into matrix form, that is AX equal to B. Here A is the m by n matrix of coefficients of variables and X is the columnar matrix for all the variables and B is the columnar matrix for the right hand side value in the constant equation. So first we have to write the matrix A, that is the coefficient of all the variables in the three constant equation. For this we have to observe all the constant equation. So first we have to observe the first constant equation. Here x1 coefficient is the 3, x2 coefficient is the 1, x3 coefficient is the 4 and s1 coefficient is the 1. Here we are not having the s2, a1 and a2. So its coefficient values are the 0. Next we have to observe the second constant equation. Here x1 coefficient is the 2, x2 coefficient is the 4, x3 coefficient is the 2 and here we are not having the s1, so its coefficient is the 0, s2 coefficient is the -1, a1 coefficient is the 1 and here we are not having the a2, its coefficient is the 0. Similarly observe the third constant equation. Here x1 coefficient is the 2, x2 coefficient is the 3, x3 coefficient is the 3 and here we are not having the s1, s2 and a1, then its coefficients are the 0 and a2 coefficient is the 1. So next x is the columnar matrix of all the basic variables, that is x1, x2, x3, s1, s2, a1 and a2 and b is the columnar matrix of the right hand side values in the constant equation, that is 600, 480 and 540. Next step is the construct the initial simplex table and this is the initial simplex table format. Here CB is the coefficients for the basic variables and B is the initial basic variables, that is S1, A1 and A2. Here we are considering the slack variable and artificial variables are the initial basic variables. So remember here we are not considering the negative surplus variable as the initial basic variables, that is in the second constraint. And CB value for these basic variables are the 0, -m and -m. For this I have to observe the objective function. Here we will get the coefficients for these variables. And next XB is the initial basic feasible solution, that is S1 value is the 600, A1 is the 480 and A2 is the 540. And here X1, X2, X3, S1, S2 and A1 and A2 are the present variables and write down its coefficient values by observing the constraint equations or matrix A. So here we have to fill all the coefficients for the basic variables by observing the constraint equation or the matrix A. So next Cj is the cost coefficient of the basic variables. For this one we have to observe the objective function and write the coefficient values of the x1, x2, x3, s1, s2, a1 and a2. So these values are the 2, 3, 4, 0, 0, -m and -m. Next step is calculate the values of Zj minus Cj and check the basic feasible solution for optimality. Here three conditions are there. First condition is if all the Zj minus Cj are greater than or equal to the 0, the optimal solution will obtain. Second condition is if at least one Zj minus Cj value is the negative, then indicated by arrow, and this column is the key column. And third condition is, if more than one Zj minus Cj is the negative values, then choose the most negative of them, and the column is called as the key column. So first we have to calculate the Zj minus Cj values for all the variables. Here Zj is the summation of multiplication of Cv value and the variables coefficients. So first we have to calculate the Zj minus Cj for the x1 value, that is Z1 minus C1 equal to the Cb x1. Here x1 is the x1 basic variable minus C1. So Zj minus Cj for the x1 variable is the 0 into 3 plus minus m into 2 plus minus m into 2 minus 2. So it is the minus 4m minus 2. Next we have to calculate the Zj minus Cj for the x2 variable, that is Z2 minus C2 equal to Cb x2 minus C2. It is the 0 into 1 plus minus m into 4 plus minus m into 3 minus 3. So it is the minus 7m minus 3. Next to calculate the Zj minus Cj for the x3 variable, that is Z3 minus C3, which is equal to the 0 into 4 plus minus m into 2 plus minus m into 3 minus 4. It is the minus 5m minus 4. Next to calculate the Zj minus Cj value for the S1 variable, that is Z4 minus C4, which is equal to the 0 into 1 plus minus m into 0 plus minus m into 0 minus 0. Its value is the 0. Next to calculate the Zj minus Cj value for the S2 variable, that is the Z5 minus C5, which is equal to the 0 into 0 plus minus m into minus 1 plus minus m into 0 minus 0, which is equal to the m. Next to calculate the Zj minus Cj value for the A1 variable, which is the Z6 minus C6, which is equal to the 0 into 0 plus minus m into 1 plus minus m into 0 and minus of m, that is the 0. Next to calculate the Zj minus Cj value for the A2 variable, which is equal to the Zj minus C7, which is equal to 0 into 0 plus minus m into 0 plus minus m into 1 minus of minus m, which is equal to the 0. Here observe that one the Zj minus Cj values are the negative for the x1, x2 and x3 variables. So among these values, we have to select the most negative value, and respected column is the key column. Here minus 7m minus 3 is the most negative value for the x2 column. So x2 column is the key column and x2 variable is the incoming variable. So x2 variable enters the basis. And next step is calculate the minimum ratio of xb divided by incoming variable, that is xb by ck. Here HB is the basic solution and CK is the coefficients for the incoming variables of the X2. So have to calculate the minimum ratio of XP divided by incoming variable for the all the rows, that is 600 divided by 1, which is equal to the 600, 480 divided by 4, which is equal to the 120. Next one is the 540 divided by 3, which is equal to the 180. Among these values, minimum value is the 120 for the A1 variable. So minimum ratio is 120 and indicated by arrow, and A1 is the outgoing vector. So basic variable A1 leaves the basis. Similarly, we have to identify the common element in the key row and key column. Here key row is the A1 row and key column is the X2 variable column, and common element for this key row and key column is the 4. So here 4 is the key element. Next step is we have to construct the new simplex table by entering the incoming variable X2. This is the old simplex table. From the reference of this table, we have to construct the first iteration simplex table. First we have to write the incoming variable X2, which has replaced with the outgoing variable A1 in the basis B, and its coefficient is the 3, which has to be entered in the CB. Moreover, we have to remove the outgoing variable A1 column in the first iteration table. Here Cj values are the same as the initial simplex table, and its values are the 2, 3, 4, 0, 0 and minus m. Next we have to modify the coefficients of variables values by the following row operations, that is R2 new, which means in the new simplex table second row equal to the R2 old divided by key element. Here key element is the 4, and second row operation is the R1 new equal to R1 old minus R2 new, and the third row operation is the R3 new equal to R3 old minus 3R2. The motive of these row operations is A2 variable is leaving in the basis and having its coefficients are the 0, 1, 0, and X2 variable is incoming to the basis, so its coefficients also have to make 0, 1, 0 by the following row operations. So first we have to look for the second row in the new simplex table, that is R2 new equal to R2 old divided by key element. Here key element is the 4. So have to look for the R2 old elements are the 480, 2, 4, 2, 0, minus 1, and we are remove the A1 column. Next one is the 0. And R2 new equal to R2 old divided by 4. Then 480 by 4 equal to the 120. 2 by 4 it will become the 1 by 2. And 2 by 4 it will become the 1 by 2. And 0 by 4 is a 0. Minus 1 by 4 will become the minus 1 by 4. And 0 by 4 it will become the 0. So same these values you have to enter in the R2 row in the new simplex table, that is 120, 1 by 2, 1, 1 by 2, 0, minus 1 by 4, 0. Next we have to look for the R1 row. So have to modify the R1 new. So by following row operation, that is R1 new equal to R1 old minus R2 new. So R1 old elements are the 600, 3, 1, 4, 1, 0 and 0. R2 new elements are the 120, 1 by 2, 1, 1 by 2, 0, minus 1 by 4, 0. Then the R1 new will become the R1 old minus R2 new, that is 600 minus 120 equal to the 480. 3 minus 1 by 2 will become 5 by 2. 1 minus 1, 0. 4 minus 1 by 2 will become 7 by 2. 1 minus 0, 1. 0 minus of minus 1 by 4, 1 by 4. 0 minus 0, 0. So these elements we have to enter in the R1 row. So that is 480, 5 by 2, 0, 7 by 2, 1, 1 by 4, 0. These elements have to enter in the first row of the new simplex table. Next we have to look for the another row operation, that is the R3 new equal to R3 old minus 3R2 new. So R3 row old elements are the 540, 2, 3, 3, 0, 0 and 1. R2 new elements are the 120, 1 by 2, 1, 1 by 2, 0, minus 1 by 4, 0. So then the 3R2 will become the 120 into 3, 360, 3 into 1 by 2, 3 by 2, 3 into 1, 3, 3 into 1 by 2, 3 by 2, 3 into 0, 0, 3 into minus 1 by 4, minus 3 by 4, 3 into 0, 0. So we have to make the R3 new equal to the R3 old minus 3R2 new, which means 540 minus 360 will become the 180. 2 minus 3 by 2 will become the 1 by 2. 3 minus 3, 0. 3 minus 3 by 2 will become the 3 by 2. So 0 minus 0, 0. 0 minus of minus 3 by 4, 3 by 4. 1 minus 1, 0. So these elements we have to enter in the R3 row in the new simplex table. So next step is we have to calculate the values of Zj minus Cj and have to check the basic feasible solution for the optimality. First we have to determine the Zj minus Cj. First we have to calculate the Zj minus Cj for the first basic element, that is x1, that is z1 minus c1 equal to the summation of cb x1 minus of c1. So which is the 0 into 5 by 2 plus 3 into 1 by 2 plus minus m into 1 by 2 minus 2. It will become the minus m by 2 minus 1 by 2. Next we have to do the Zj minus Cj, we have to determine for the second one, that is for x2 variable, that is z2 minus c2 equal to summation of cb x2 minus c2, which will become the 0 into 0 plus 3 into 1 plus minus m into 0 minus 3. So which will become the here 0. Next we have to look for the another basic variable x3, that is the z3 minus c3 equal to summation of cb x3 minus c3, which is the 0 into 7 by 2 plus 3 into 1 by 2 plus minus m into 3 by 2 minus 4. So which will equal to the minus 3m by 2 minus 5 by 2. Next we have to look for the next basic variable s1, that is the z4 minus c4 will become the 0 into 1 plus 3 into 0 plus minus m into 0 minus 0, which is equal to the 0. Next we have to look for the next basic variable s2, that is the z5 minus c5, which is equal to the 0 into 1 by 4 plus 3 into minus 1 by 4 plus minus m into 3 by 4 minus 0, which will become the minus 3m by 4 minus 3 by 4. So next we have to look for the next variable, that is the a2, so which is equal to the z6 minus c6, which is equal to 0 into 0 plus 3 into 0 plus minus m into 1 minus of minus m, which is equal to the 0. So here we have to observe we have to select the most negative value. Here negative values are the minus 3m by 2 minus 5 by 2. Another one is the minus m by 2 minus 1 by 2. Next one is the minus 3m by 4 3 by 4. Among these values, most negative value you have to select. Here most negative value is the minus 3m by 2 minus 5 by 2. So that is the x3 column. That x3 column we are calling as the key column, and x3 variable is leaving to the basis. So next step is we have to calculate the minimum ratio of the xb divided by incoming variable. For this one, first we have to do the, for first row, xb divided by incoming variable. For the first row, xb value is the 480 and incoming variable value is the 7 by 2. Then the 480 divided by 7 by 2, it will be equal to the 960 divided by 7. So next xb value is the 120 divided by 1 by 2, which is equal to the 240. Next xb value is the 190 divided by the 3 by 2, which is equal to the 120. So among these values, you have to select the minimum value. Here minimum value is the 120 for the third row, that is the A2 row. So minimum ratio is the 120 and indicated by arrow, and A2 is outgoing vector and basic variable A2 is leaves the basis. So next we have to identify the key element, which is the common element in the key row and the key column. Here 3 by 2 is the common element in the key row as well as the key column. So 3 by 2 is the common element, that is the key element. So we have to go for the next step, that is the construct the new simplex table for the second iteration by entering the incoming vector. This is the first iteration simplex table. From the reference of this table, we construct the second iteration simplex table. First write the incoming variable x3 in the basis B and writes its coefficient value is the 4 in the CB. And remove the A2 column in the second iteration simplex table. Here Cj values are the same as in the first iteration table, that is the 2, 3, 4, 0 and 0. Next we modify the coefficients of the variables by the following row operations, that is R3 new equal to R3 volt divided by key element. Here key element is the 3 by 2. Then R3 new equal to R3 volt into 2 by 3. Second row operation is the R1 new equal to R1 volt minus 7 by 2 into R3 new. Third row operation is the R2 new equal to R2 volt minus 1 by 2 into R3 new. So let's see the first row operation, that is the R3 new equal to R3 volt into 2 by 3. Here R3 volt elements are the 180, 1 by 2, 0, 3 by 2, 0 and 3 by 4. So into 2 by 3 will become 180 into 2 by 3, that is the 120. 1 by 2 into 2 by 3, it will become the 1 by 3. 0 into 2 by 3, it is the 0. 3 by 2 into 2 by 3, it is the 1. 0 into 2 by 3, it is the 0. 3 by 4 into 2 by 3, it is the 1 by 2. So enter these values in the row 3 of the new table. Next we have to look for the second row operation, that is the R1 new equal to R1 volt minus 7 by 2 into R3 new. So R1 volt elements are the 480, 5 by 2, 0, 7 by 2, 1, 1 by 4. Similarly, R3 new elements are the 120, 1 by 3, 0, 1, 0, 1 by 2. Then the 7 by 2 into R3 of the new element is the 120 into 7 by 2, 420, 1 by 3 into 7 by 2, 7 by 6, 0 into 7 by 2, 0, 1 into 7 by 2, 7 by 2, 0 into 7 by 2, 0, 1 by 2 into 7 by 2, it is the 7 by 4. So next we have to do the R1 volt minus 7 by 2 into R3 new, that is 480 minus 420, 60, 5 by 2 minus 7 by 6, 4 by 3, 0 minus 0, it is the 0, 7 by 2 minus 7 by 2, it is the 0, 1 minus 0, it is the 1, and 1 by 4 minus 7 by 4, it is the minus 3 by 2. Enter these values in the row 1 of the new table. Next to see the another row operation is the R2 new equal to R2 volt minus 1 by 2 into R3 new. Here R2 volt elements are the 120, 1 by 2, 1, 1 by 2, 0, minus 1 by 4. And R3 new elements are the 120, 1 by 3, 0, 1, 0, 1 by 2. Then 1 by 2 into R3 new is the 120 divided by 2, 60, 1 by 3 divided by 2, it is the 1 by 6, 0 divided by 2, 0, 1 divided by 2, it is the 1 by 2, 0 by 2, 0, 1 by 2 divided by 2, it is the 1 by 4. Next we have to do the operation is the R2 new equal to R2 volt minus 1 by 2 of R3 new, that is 120 minus 60, it is the 60, 1 by 2 minus 1 by 6, it is the 1 by 3, 1 minus 0, it is the 1, 1 by 2 minus 1 by 2, it is the 0, 0 minus 0, it is the 0, minus 1 by 4, minus 1 by 4, it is the minus 1 by 2. Enter these values in the row 2 of the new table. Next step is we have to calculate the values of Zj minus Cj and check the basic feasible solution for the optimality. First we have to go for the variable, first variable, that is the x1, that is the z1 minus c1 equal to the 0 into 4 by 3 plus 3 into 1 by 3 plus 4 into 1 by 3 minus 2. This value is the 1 by 3. Next to second variable, that is the x2 is the 0 into 0 plus 3 into 1 plus 4 into 0 minus 3. Its value is the 0. And next to third element, that is the x3 variable, that is the 0 into 0 plus 3 into 0 plus 4 into 1 minus 1. It is the value is the 0. And for the next variable s1, for that one zj minus cj value is the 0 into 1 plus 3 into 0 plus 4 into 0 minus 0. It is the 0. And last element, fifth element, that is the for the s2 variable z5 minus c5, which is equal to the 0 into 3 by 2 plus 3 into minus 1 by 2 plus 4 into 1 by 2 minus 0. Its value is the 1 by 2. Here observe that one the all the zj minus cj values are the positive values. So if all the zj minus cj value is greater than or equal to 0, then optimal solution is obtained. So here we obtained the optimal solution. So if all the zj minus cj values, positive values, which are greater than or equal to the 0, and also artificial variables a1 and a2 have been removed from the basis. Here observe that one we are not having any artificial variables. So then the optimal solution is arrived. So here we are arrived the optimal solution with the x1 equal to the 0, because there is the no x1 variable in the basis. So x1 value is the 0 and x2 value is the 60 and x3 value is the 120. Then I have to substitute in the objective function, that is z equal to 2x1 plus 3x2 plus 4x3. Here substitute x2 value is the 60, x3 value is the 120. Then we will get the z value is the 660. So this is the solution, and thank you.